And hi and welcome from my side as well. I'm very happy to be here. And yeah, this session is going to be about when, why, and how to apply the CQRS buzzword. So a buzzword-driven session. My name is Sebastian Daschner. I'm German. I'm from Germany, and this is actually my very first time here in Russia. And I really enjoy it so far, what I've seen. So this is my name written normally, and this is my name, as far as I know, written in Cyrillic letters. And yeah, I'm doing a lot of things with Java, so I'm a Java consultant, freelancer, trainer, and author. I help standardizing the future of Java Enterprise. I'm part of the JCP and part of 2 or 3 expert groups in CQRS and JSMP. And I'm a regular, conference speaker on conferences like this. So I do a lot of Java things and Java Enterprise things. And yeah, and also, as it turned out, I just published a book about Java Enterprise, architecting modern Java EE applications, showing how you do Java EE in the modern world with cloud and containers and Java EE 8 and so on and so forth. So you can also check that out if you like. And then, about the CQRS principle. So who of you has heard the term CQRS at least, or even used it? Hands up. Okay, that's good, not too bad. For those of you who do not know the term, don't worry, I will explain what it is about, and especially I will explain the motivations, so why we as developers should care about these principles. And it all goes back to how we normally tend to build enterprise applications. In normal enterprise applications, what we have a CRUD-based model, right? So we store our data as the current state in normally the database, right? A relational database normally. That means we have our application, and that application has a current state, right? And once we change something in the application, we have a new current state. And the old current state is, first of all, forgotten, right? And we have to somehow deal with, being consistent. That's why we have things like ACID transactions and so on and so forth, to maintain all the state in our enterprise application, right? And however, this approach has some shortcomings. So what that is, the CRUD approach, create, read, update, delete, CRUD, has some shortcomings such as reproducibility. What does this mean? Well, once we have a state in our application and we have a new state, first of all, the old state is forgotten. So we cannot reproduce how our system got into in its current state. Right? And it's in some state, and we don't know how it got there. We don't know the history, first of all. And that's first of all a shortcoming, right? And then, because of the fact that we have to be consistent, we want to be consistent, we have to, compete with transactions. Because we are in an enterprise environment. We have enterprise applications, and we have potentially multiple clients coming in at the same time and wanting to change something. So we have to deal with that, and that means we have to synchronize. And because of that synchronization, we ultimately cannot scale, or at least not scale infinitely, right? Because at the very end of the day, we have one database that needs to synchronize something when we want to do, simultaneous updates, right? And that's also another shortcoming of the CRUD-based approach, because we always have a relational database sitting in the middle of an enterprise system, and that will maintain this state, right? And now, the CQRS principle is basically how to deal with that situation and an approach to do that differently in a distributed system environment. And first of all, to get the motivations, I will show you 2 different motivations that ultimately lead to the CQRS principle. The first one is event sourcing, and the second is event-driven architectures. First of all, event sourcing. Who of you has built event-sourced systems? Hands up. Okay, quite a few. Event-sourced systems are quite common, more or less. They, first of all, don't have to do anything with distributed systems. But how do event-sourced systems work? Well, we don't store the current state as we would in a CRUD-based system. Rather than, we store atomic immutable events, and then we calculate the current state based on the events. A prime example are bank accounts with money transactions, right? You have money transactions plus $100, minus $50, plus $20. And if you want to see the current balance of your account, why you have $335 on your bank account, you start from 0 and you apply plus 100, minus 50, and so on and so forth, right? And that's an event source system. You apply all these transactions, all these immutable events that happen to your system, and then you calculate the current state. Why do we want to do this? Well, first of all, this gives us, for free, full context and full history information. If you want to know why you have $335 on your account, you just look at the recent money transactions and then you know why, right? You have the full history right there. And that's the core of your system. That's part of your system. Your whole data just comprises of these events. And then, well, as a nice benefit, you can also do some statistics and testing based on these data. For example, these data, all these events, these immutable events, comprise everything that happened to your system. So everything that happened to the system that has been running for, let's say, 2 years in production is stored in these events. So that means if we want to have end-to-end use cases, we just take production data with all these events, rewind them, put them into a test system, and then voila, we have perfectly fine production test data, for example. That's a nice scenario. Another one is one that I would call future-proof use cases. What does this mean? Well, imagine your project manager comes to you 2 years after that system has been running in production and asks you, well, how many users did sign up on today's Friday, on a Friday? And then you say, fair enough, we don't know. That was never a requirement, right? We don't have this information. Well, in an event source system, you do have this information. Because if you store everything that happened to the system, you just take all the user signed up events, look at the timestamp, and then you can calculate how many users actually did sign up on a Friday. So what you're doing, you store everything that happened to the system in an atomic and immutable way, and then you can use that later on, which is a very big benefit, right? And now about, well, the second approach, event-driven architectures that also lead to this CQRS principle. But first of all, let me tell you a story, because that's going to be about being eventually consistent and dealing with this fact that we normally build enterprise applications that have to be consistent, right? And I want to tell you that the real world, where we're living in, is actually not consistent. Just one example, and then you can derive some, well, business knowledge out of that. Anyway, imagine you're in a restaurant. So you're hungry, you go to a restaurant and you want to order a meal, right? Let's say you want to order a burger. So what you do, you go to the restaurant, you sit down at the table, and you tell the waiter, I'd like to have a burger, please. And what the waiter says, well, yes. Nods and accepts your order, right? And now you think this is a consistent transaction, but actually it's not. Because just you ordered that burger doesn't mean you will get one. Because a lot of things can go wrong in the meantime. For example, you ordered a burger, everything's fine. Now what happens, the waiter goes to the kitchen and tells the chef, one burger, please. And then the chef says, Niet, sorry, we're out of burger, I can't help you, we don't have ingredients. And now, even though the waiter accepted your order at the first place, they have to come back and tell you, sorry, sir, we're out of burger, right? And that's what happens. So now what happens? Well, error, exception, you angrily run out of the restaurant, right? Or the waiter tells you, well, it's such a nice day, don't you want to have a salad instead? So whether this is a good substitute or not, well, but this is what happens in the real world, right? You have to somehow talk to each other. You have to deal with this situation, right? And that's how the real world works. So basically, collaboration is needed. We have to talk to each other. And you're constantly trusting on outdated information. Because the waiter now knows we're out of burger, and maybe in the same second, a delivery truck comes and brings in new ingredients. So now it's actually possible to do burger again, right? So you have to deal with that situation anyway. And you have to deal with compensating use cases for exception handling. Because how would a consistent restaurant look like in the real world? How would that look like? You go, sit down at the table, and say, I'd like to have a burger, please. And now you want to make sure that you really get your burger. So now what happens? The waiter tells, everybody stops, nobody moves. Wait, sir, wait. I'll ask. You hold the conversation, He asks at the kitchen, 1 burger please. The chef says, yes, it's possible. The chef prepares the burger. Everybody has to wait. Now the burger is finished. The waiter comes back and tells you, yes, it's possible to have a burger. Here is it. And then you can continue. That would be a consistent use case, right? Of course, this would not scale. This would not work. So we have to deal with this fact. Or how I would put it, the real world is all about collaboration. We have to talk to each other. Then hopefully good intentions. Because that's what it is, ordering a burger. It's first of all an intention to do so. It doesn't mean you will get one. And then eventually dealing with these issues. Because something will happen. And now about event-driven architectures. Because that's, well, connected to this. Event-driven architectures, first of all, means we have several systems involved. We have several peers. And that's important. Because only if we are in a distributed environment, we have to deal with this. If you don't distribute, then you don't have to care about this, right? Because, well, if you don't distribute, it's easy. You can just scale with one system, right? So you have to have several systems involved, and now these systems talk to each other via publishing events. That's how this works. And what you're doing, you're basically splitting up business transactions, such as ordering a burger, into smaller ones that are still eventually consistent. So what you're doing, you introduce this asynchronicity, and then you're introducing, by doing so, eventual consistency, which is normally fine. Because eventually, you will be consistent. You won't be consistent all the time, but we know this from the real world already, right? Let me give you another example with some nice ASCII art pictures. Let's talk about coffee. Another use case, not a restaurant, but a coffee shop. Let's say you want to order a nice cup of coffee, right? And now the coffee shop is a distributed system, consistent of an order system where you order, consistent of a bean storage that tells you how much beans are in the store, and consistent of a barista, the hipster guy who brews your coffee, right? So what you do, you want to order a coffee, so you go to the order system, that's where you order, and say, order coffee, please, I'd like to have a cup of coffee. Now what happens, the order system needs to know whether there are beans in stock from the bean system, so you could synchronously call the bean system, ask about the beans, then wait. Bad idea. Distributed transactions, right? Does not scale. What we do instead, we say order coffee, and now event, order placed. That's it, done. You fire an event, order has been placed. That's a fact. It happened in the past, it's immutable, order has been placed no matter what happens. Even if it's not possible to get the cup of coffee, still the order has been placed. And now, the client can come back, does something else, wait on a smartphone, and now, asynchronously, the bean system can consume this event and say, validate the beans, right? A new order has been played, let's see whether this is possible. You validate the beans, and then what happens? A new event arises, order beans validated, that's a yes, or something like order failed due to insufficient beans, if it's not possible, right? So what you're doing, you're communicating via these events. Now the bean system fired another event, order beans validated. Now, also in an asynchronous way, your order system can come back and say, oh, that's great, now I can accept the order. Now I know that it will be possible, and now if the client comes back, they can tell me, well, your order is at least accepted, it's possible, so it will be done soon. And only now the barista system, because it's only interested in accepted orders that are possible, will start the coffee brewing process, right? So coffee brew started, that's another event, and so on and so forth. We can now update the order again, say, okay, the order now has been started, and then beans will be fetched, and so on and so forth, and eventually the coffee will be finished and delivered. And now, order delivered, that's the very end of your business use case. You say order coffee at the beginning, and now the order has been delivered. So what we did, we are splitting up this whole use case where we have several systems involved into smaller ones. Because that's the interesting and important thing, we are still consistent eventually. So all these events have to be published reliably. What does it mean? Well, It's fine if you order the burger or the coffee and you will get your dish. And it's kind of fine if they say it's not possible, but it's not fine if they forget about your order. If they order the system and they don't know you because the event has been lost somewhere. So it is very important that everything, all these events are published reliably in every step. So you still have transactions, they are just, well, split up into several ones. And by doing so, because now we have this asynchronous processing, we are able to scale horizontally. Because you don't have to wait for each other, you don't synchronize, you just, well, waiting, and once an event arrives, everything happens here, and you see this ping-pong effect there. And now, about this buzzword CQRS, that stands for, long word, Command Query Responsibility Segregation. Interesting word, that could be German if you put it together. What does it mean? You're basically separating writes and reads. You're separating concerns for commands, for writes, from queries, reads. So everything that happens in our system has to emerge from an event. That's the part of the event sourcing part, where the CQRS principle is based. And all these events, well, are published through the systems, so the system communicate via these events, event-driven architectures. And together, well, that means a command changes something, right? So a command produces events. And a query just reads. A query is not allowed to change anything. So what happens? A command produces events, or, well, throws an error, or nothing happens. But basically, you call a command, and an event arrives. In Java, that would be something like void do something, right? So a method signature where you're not allowed to return any data, but you change the state of the system. A query, the read side, is a getter. You say string get something, but you're not allowed to have any side effects. You're just returning data. And what happens? Well, these events have to be handled reliably, as we just saw, and you derive the current state solely from these events. To get a better idea, let me give you some more ASCII-odd pictures. This is the rough architecture of such a system. So what we're doing, we're splitting up our system into concerns for commands and queries, a command service and a query service, and these solely communicate via these events that are published through an event hub or event store. And these events, again, are the golden source of our system. Everything is derived from the events. So that means command services are allowed to publish events, and all these events will be, well, published to all the consumers to update their internal status. Because what they do, you see this in database, they have internal state representations. Could be represented as database, could be in memory, could be whatever they like. And the important thing is, these databases over there are totally independent. They're solely bound to their each individual instance. So that means the systems don't communicate through each other, only through the event store, and each and every instance has its internal representation, for example, a database. And this representation is where the current state is stored. So for the example for our coffee order, let's see the same example here, what happens to a system. So let's say we want to order a coffee, right? So that means now we go to the command service, since we want to change something, right? We want to change something in our system, and tell it, well, please place an order, right? We want to have a new coffee order, go there and place it. And now what happens? The command service can do some validation against its internal database, but only its own database, if needed, and then eventually an event will arise. Order placed. That will be published to the event store, and again, this has to be published reliably, and then that's it. The client returns, can do something else, and the event is in the system. The event, order placed, is in the event store. And now, this event will be published to all the consumers that are in the system, right? So all the consumers update then their internal representation at their very database instances. That can be used, for example, if the client can come back to the query system now and can ask for the current state of the system, the current state of the coffee order, right? Give me the coffee order, and now the client will get the latest representation that has been updated from some event from the query system. And also the command service will update something if they have some validation, whatever database. And that means now the change is in the system and it's replicated in all the internal representations. And in the same way, because ultimately we want to get our coffee right, we will have some event handling mechanism that will be called, of course, on the command service side, will consume that event also reliably, and will then potentially call a new subsequent command and do something else, right? That also can emerge in a new event and so on and so forth. So that's basically how it happens, how the workflow works in this case. So what we have now, basically doing so we can scale independently. That means since all the instances for both the write and the read side are just, well, connected through the event store and event hub with a message-based, message-driven solution, right? We can scale. We can just fire up new instances. And also, that's quite interesting, we can optimize each side individually. For example, let's say it makes more sense on the read side to introduce whatever, a NoSQL database rather than a relational database for the internal representation. Or maybe we want to have one side just with an in-memory solution for some reason. We can individually optimize each and every side. They're just coupled through the event handling mechanism. And, well, we can also scale independently from the read and the write side. So that means we can fire up many more read instances than write instances. Why do we want to do this? Well, in a typical enterprise scenario, the number of reads highly outperform your number of writes, typically. So that means if you have a web application, you're typically reading far more often than you're writing, right? You constantly do HTTP get something, you constantly browser F5, and once in a while you write something. That means we can fire up many more read instances that then all can serve all these read queries that come from the client. That's a nice benefit as well. And also it solves the potential problem of event sourcing with scaling. What does this mean? Well, in an event source system, imagine again this bank account, and you have all your money transactions, plus 100, minus 50, and so on and so forth. And once your system has been running in production for 2 years and longer, if you would always calculate the current balance by starting from 0 and calculating all these transactions each and every time, your system gets slower and slower and slower, right? Because you have more and more and more transactions to calculate. Well, what CQRS does with all these internal representations in these databases, it solves that problem by only applying the latest change, the latest diff in the system, by the latest event that comes in, right? Because you don't always go back to 0 and start from scratch. You start from the latest state that is in the current representation, and you just apply the latest event, right? You could, if you like, throw away the current state, start from 0, you have to go and you have to come to the same result, but you store it for optimization. And also, as a nice benefit, you get read-side failover capability in a CQRS system. Because what happens in a CRUD-based system if your database goes down? That's it, right? You can't write, you can't read, you can't do anything because you cannot store and read state. In a CQRS system, what happens if your event store goes down? You can still read, right? Because what happens, you cannot change anything in the system, you cannot produce new events, but all these read instances have still their internal representation in their database. And if you query one, well, you get the representation from the database or from in-memory or whatever. And that is a big benefit because, well, you can still read. You cannot change anything, but you can still read. Fair enough. So, do you have any questions so far? How long? Oh, sorry? Well, you basically store these forever. In this approach, yes. It depends how much data you have, basically. So what you could do is introduce something like a snapshot, where you say you not always start from 0. For example, your bank account does probably do this.
So you can only see your bank transactions from the last 90 days or something, depending on your bank. The usual case, I would say there isn't a usual case, it depends on your business, what you're doing. So as the easiest approach, you would store everything, and you would go until back in all the time, so you have all these events. And normally that's fine in the amount of data. But then again, it depends on what you're doing. And then also it depends whether you actually need to go all the way back in time and retrieve all these events in your live system, or if you can just store it away and take a snapshot as the new zero. That's basically it. Yes?
Event-sourced model is not applicable.
Oh, good question. An example when the event sourcing, was it the event sourcing or the CQRS in general model is not applicable? Both probably, okay. So, a very good question. When is the CQRS model, first of all, not applicable? When you don't distribute. If you don't have distribution, if you don't have microservices, don't do it. Why? Because it adds up, you will see this in the live demo, in the coding right now, it adds a lot of complexity. You have to have this message hub, you have to deal with all these, use cases, with all these asynchronicity, and if you don't have this, don't do it. If you can live with a CRUD-based system, that's fine, that's good, because that's simpler. You will see this in the demo. For the event sourcing, if you want to have the benefits of event sourcing with the history and the context information, you can still do this even if you want to be consistent. So for example, we've done that for years. You can build event source systems based on a consistent CRUD-based approach by just storing these events in a relational database and then just calculating manually. Of course, it will not scale that much because you still have a single monolithic application or at least database in your system, but you get all this history information. And if that's fine in terms of scalability, if you don't need to distribute, that's good. Do this. Again, your question when not to do event sourcing, well, that depends basically when you don't need it, right? I would argue you can potentially always need it because then you're future-proof by storing all these events, all these information in events. So basically what you're doing, if you say we don't want it for simplicity, we just go with the CRUD-based approach, also fine. We have, done this for years, forever, right? Building typical enterprise applications. But then you're just giving away all this extra information that happened to your system. Because what happens once a use case comes in, you just store, the new information, you store the new state, and everything before is thrown away. That can be fine, depending on what you're doing. It can be totally fine. So definitely an event-sourced system is also a little bit more overhead than a CRUD-based approach. Fair enough. But you're also giving away information. So that's basically the trade-off. And you have to calculate, what doesn't make sense for my specific solution? So that's basically the deal. But with the distribution, event-driven architectures and CQRS only do it if you need to distribute. That's very important. Yes. The question was whether it simplifies the overall architecture. Yes, it does. And it is one approach to deal with this situation. So the situation is, we want to have the history and context information, everything from event sourcing, and we need to deal with, scalability. And that is one approach to tackle that.
What kind of storage do you recommend for CQRS?
I'm here. I didn't know where it came from, but what kind of storage? Storage in terms of internal representation, you can use whatever you like. For example, a relational database. Storage in terms of event store, I'm using Apache Kafka in this case. What I would recommend, that also depends a little bit on what you're doing and which technology you're familiar with. But Apache Kafka is one distributed eventing solution to deal with that also can store and handle a lot of data.
Hello. I'm here.
Oh, yeah.
So imagine you have a large system with a lot of types of events. Okay, and what if you decide that you don't need some types of events? How to throw it out from event store, and how to deal with this?
Yeah, that's a good question. So that basically means you want to change something in your event domain model, right? And that's in general, first of all, a bad idea. Why? Because that means you're kind of you're kind of changing the history, right? That means you had a type of event, you had some events that happened in the past, and now you basically saying these events are not true anymore, right? Because now I want to throw them away. So something happened in the past, and now it's not valid anymore, right? Somehow. The same is true if you want to change a model, right? If you say, now we want to change our domain model, like the core of our system, the model of the events, that means, well, was everything we've done in the past not true because something was missing or something was wrong, right? So that's basic. First of all, the business question you would have to ask yourself. And then, depending on that answer, you would say, okay, either that is actually a different use case, a different approach, and we model it differently in another event type, or by adding something and not just using the thing anymore. So throwing away data or changing history is always, first of all, dangerous, I would say, and then it depends on the answer the business department gives, basically. And then if you really have to do this, that, well, would mean you go to your event store and you really have to change its core. So basically you have to throw them away and redo it by, well, changing all the events that are part of your system. But you have to be aware, then you're changing history. And then you really have to know what you're doing, right? So you say, okay, we did a mistake, for example, or we modeled it in a wrong way, could be, of course. And then we need to change that at the core of the event store.
Okay, and if you decide that history is not mutable, you just leave this with these sort of events and just don't use it. Okay, yes?
For example, yeah, it depends on your business. If you say this is not used anymore and we still want to have it in our history because that was part of the history. Yeah.
One more question, please. Am I right we should use one consumer group for each reader and one more for command service? Or we could decrease the number of consumer groups?
Yes, basically that's, I don't know where the question came from. Oh, from there, okay. Basically, yes, that's what I'm doing. And then I will show this as part of the demo, what I'm doing with Apache Kafka consumer groups, yes. So then we can have more questions later. Let's go to the demo. So what I have, I show CQRS with Java EE and Apache Kafka for you. So what I have is a, well, scalable coffee shop application. So basically all these things I just talked about and showed in the code slides with the coffee shop demo I have here in Java code. So this is already a good example, right? Normally I would love to live code everything from scratch for you. But you see, and you will see it in the code, that the CQRS approach is actually quite an overhead. So I could not live code this in 60 minutes, right? Because you have to have a lot of classes, you have to add all these events and all these types, and, well, have to deal with Apache Kafka and the messaging solution and so on and so forth. So this is a pity, but I will go through that, through the code at least, and explain these things that I'm doing, and also, of course, having a live demo. So that is the project. It's on GitHub, Scalable Coffee Shop. That comes with, you can already see that. I will open it bigger. With 3 systems, named the barista, the beans, and the order system, what you just saw. These will be, well, built and published as 3 Java EE applications, running in 3 independent instances of application servers, running in 3 Docker containers, so I have a Docker set up here locally, and so on and so forth. Why 3? Why not 6? Well, splitting up these concerns for writes and reads, right? It would make sense, or it would be possible to split up the instances for reads and write. But you don't have to do this, of course, right? You can basically do an order system that I'm doing and both deploy the read concerns and the write concerns in the same system. It's fine if these 2 don't communicate with each other, only via the valid way through the event store, right? And this is what I'm doing for reasons of simplicity. So I will show you the order system as an example. So what I have an endpoint that talks with HTTP. So all the client communication is done with HTTP, with a REST approach, with, well, JAX-RS in my case. And then, well, you use this endpoint to create some orders in this case and to read the status of the orders, right? And they internally use some command and query system service. So that is already the approach. You see it, it's in one resource, both for reads and writes, but then it's totally split up. They don't communicate with each other, the write and read concerns. So let's quickly go through it. If you have any questions, then feel free to ask. This is CQRS, well, the standard to develop REST applications. I don't know if you're familiar with that. But that basically means we have some JSON input with some coffee order, and we do this and that. And ultimately, we want to place that order at the coffee service, right? Place order with this information. And for us, we don't want to validate something. That just means now we want to publish that event, right? You remember, order placed. So this is what we're doing here. We take an event producer. I will show this in a second. And then publish that event. You can also see the method signature, void, do something, place order. As soon as this method returns, we can be sure, or we must be sure, that the event is in the system, the event has been placed reliably. That's it. Place order, let's say that works, and then that's fine. We can come back, response accepted, HTTP 202. Thank you, come back later. Your order is in the system, but I can't tell anything about it now. We include some randomly generated UID to tell where to come back later, and that's it. Now the client can return, do something else. Later on, the client can come back using this ID and ask for the status of the order. So that's now the query part of that system, right? And now the query system can be asked, give us the order to this ID, please. Query service get order. And what the query service does, if you remember, it takes the internal representation and returns that result, right? And the internal representation could be many things, for example, a relational database or a hash map. That's the easiest way to do it in memory in this example. So basically what we're doing, we have a concurrent hash map here that will be updated each and every time an event arises, and that will be used to return the current status. So what happens, once Apache Kafka produces a new event, we will listen to that event, and if you're familiar with Java Enterprise, we already have quite sophisticated eventing feature, namely CDI events, and this is what I'm doing here. So basically every time a Kafka message comes in, a CDI event will be thrown with the right information. For example, observes order placed. That's what happens. The order placed event now is in the system. And then, well, we put in some new coffee order into a hash map, or if order will be accepted later, we update the status and so on and so forth. And then this means we update the status of our domain entity, of our domain representation, the coffee order. That will be stored in memory. If you want to introduce a relational database, a real persistence, fine. That's the right place to do so. You just call the entity manager and store it, same story. And you will use that later on once the client asks for the status. And that's it. You return it, done. And I will show this more in a second. But quickly, how the updating part is done. So basically, we have a consumer, an updating consumer that, well, connects to Apache Kafka, that is roughly part of the Kafka API, and says, once something comes in, throw a new event, fire a new coffee event in the correct type that will be deserialized. I'm using JSON to serialize all these events, but this doesn't matter, just from an architectural point of view. Once a new event arrives, a CDI event will be fired. And then, well, we can listen to these events that you saw there. Now, before we do further talking, let's show the demo, right? So some coding here, what I have. These are 3 command line instances for orders, beans, and barista system. So that system comprises, well, these 3 things. And I also have a local Apache Kafka cluster running, well, in a Docker container as well. So what I'm doing, I will build the first and the second and the third application to then connect all of them against the Apache Kafka run cluster that also runs locally. And then I can use that, right? And now I have 3 applications running plus my Apache Kafka cluster, and I can take a new command line to now, well, order some coffee, right? Via REST. So I will use some REST client. I like the command line. I use curl. So I use curl to place a new order. Just go through that quickly. That means we post a new order at the system that runs localhost port 8001. That's the order Docker container for the order system. And I post a new, well, application JSON, a new JSON with beans from Colombia. So I want to have an espresso with beans from Colombia, right? That will be ordered in the system, and then the system will tell me whether this is possible, right? So let's do it. Let's fire this against the system. We just saw in the example HTTP 202 accepted, thank you, come back later. The order's in the system, hopefully. And now it will tell me where to come back later to ask for its status. So the location, here you see it in the HTTP location header, and now I can click on the link or follow up with that resource and ask for the status. And it will tell me, oh, cancelled. Why is it cancelled? Well, the first system produced that event, order placed. The second system, the bean system, sees, oh, order placed, that's fine, but I don't have beans in the system. Why? In memory, hash map, right? So the second system is still empty. Actually, we have to store beans first. So what we need to do, we need to go to the second system, to the bean system, and put in some beans, right? Otherwise, we can't have our coffee. So basically, we want to post some new beans first. We go to the second system that also has an HTTP endpoint, 8002, that's the second Docker container for the beans, and we post some 10 beans of Colombia, right? Let's do it. 204, no content, fine, thank you. And if we now ask for the beans, which is also a hash map, we have now 10 beans from Colombia. Fine, great. If we now ask for a status again, of course it's still cancelled. That's gone, we need a new one. Okay, let's post some new coffee, right? Same story again, we want to have a new coffee. Now this time we ask, we get the same response, 202 accepted, because it's also again accepted. That was always true. Now we have a different order, and now we can ask that order to, oh, started. Now our coffee brewing process has already been started. And if you watch, I put in some output of these events that happen. Basically that means order has been placed, and then order has been accepted, and so on and so forth. And now the barista guy is basically a timer that randomly decides whether your coffee is finished or not, and now you see it's finished, and then soon it will be delivered as well, which you remember is the final outcome of our business transaction. Cancelled is also a final outcome. And then ultimately now it's delivered, fine. Now that's the end result of our transaction. Now our coffee is finished there, right? And let's do something fun. Let's kill all the containers here. So now all the systems are gone. No more coffee. And now let's respawn them. I always rebuild them again, but this doesn't matter. Let's fire up new instances of these systems. So what I'm doing, just as an example, just to showcase it, I use this in-memory example because I tell Kafka all the time, please redistribute the whole history, redistribute everything you know to me, so I can rebuild my internal representation, because I only have that in memory. So what happens, you already see it in the output, all these events will be redistributed. So now I come back to the system and ask for the same event, and with the event that has been created in memory, with a randomly generated UUID, I get the same output, order delivered, orders in the system. Same is true for this unlucky order that has been cancelled. So now I come back to the Apache Kafka cluster, which is the golden source of truth. I can ask for the whole history, and I can rebuild that history. And, well, you see it's of course not production ready. Why? If I come back to that and do this all the time, and once my system has been running for 2 years, there's a lot of events in the store. And then on application startup, the startup of my application gets slower and slower and slower, right? Because we have to redistribute all these million events. Of course, in an enterprise production system, what you would do, you would take this internal representation and well, replace the hash map with a real database, with real persistence. So then you don't have to come back and tell Kafka, please redistribute everything. Just redistribute what's new to me, right? And then, well, you can do so reliably, and you don't have to recalculate how I'm using these consumer groups. Because I always told you in the slides, these events have to be published reliably. So what does this mean? If we look into the order event producer, so there is an event producer here that's used in the command service to publish new events. That is the Kafka API, and actually right now I'm using Apache Kafka 1.0 that has been, I think, published 2 days ago. And since 0.11, Kafka supports transactional producers, which we need because, well, we want to produce the events reliably. We want to make sure once an order comes into the system, that order will be placed reliably, right? And therefore we need the transactional producing of the system. And then we produce the event, and then it will be consumed. And the consumption happens in several so-called consumer groups. Some more nice ASCII art pictures. So what's that? We have at least 3 consumer groups, 1 big event handling consumer group, and then each and every consumer group per instance. Why? That's now Kafka specific, and this is how Kafka handles all this. You can configure Apache Kafka so it has exactly once semantics. What does it mean? Well, a message gets exactly once delivered, right? Because you don't want to have it at least once or not at all, or maybe you want to be sure. That's what it is about. And it can be configured that you have exactly once semantics per consumer group. So what you're doing, you have several consumer groups, and now in my case, I want to make, well, a consumer group for the updating part that updates the internal representation, and I want to have separate consumer groups or 1 consumer group for the event handling part that fires new events. Because what happens if you restart the system and then you have these new orders and then you have 2 coffee orders and 4 and 8? No, that would be bad, right? So basically what you're doing, the event handling part that fires new subsequent commands, subsequent events, will connect against the event handler group. This is not redistributed. If that would be redistributed, you end up with 2 coffee orders, 4 coffee orders, so on and so forth. So you only do this once. But you do the updating part each and every time a new system comes up. So a new system, in my case, because it's in memory, will connect against, well, a new consumer group. In this case, if you have persistence, then of course you use the same consumer group. And that consumer group knows what type of, which event you consumed last. And you can commit to these events. That's what you have to do, right? To be reliable. And then these will be redistributed once you start up new applications. So basically what happens, a new application connects against, in my case, for the in-memory approach, a new consumer group. The new consumer group has no last published events there. This will be redistributed, and then, well, you have the new state there. Because what happens, you updating consumer will just update the internal state. You fire these type of events that will be updated here in our event representation. That's the updating part. That's good. We need this for each and every time because each and every instance wants to have the latest status, right? So we have a lot of consumer groups for this. For the event handling mechanism, or the event handler, we do a similar thing. We'll have a single consumer group. Why? Because all these things here, all these CDI events, will trigger new subsequent commands at the command service. And this thing needs to be only executed once. Once per cluster. I come to that in a second. So that means once we start up the whole system, we don't have 2 and 4 and 8 coffee orders. We only have it once, and that's it. Never again. and that will not be reset. We don't redistribute this consumer groups, only the other ones. And that is also the reason why 2 applications, or 3, or all of them connect against the event handling consumer group. Otherwise, if you have 2 order instances, or 2 beans instances, you won't end up with 20 beans, or 2 orders, or 4 orders, and so on and so forth, depending on the number of instances. So only 1 instance, or more precise, exactly 1 instance per time, has to handle events to trigger new subsequent commands. That's important, otherwise you will end up with an inconsistent state. And in my case, I use Apache Kafka consumer groups to do so. So that means I have a single event handling consumer group, no matter how many instances I have. So I could easily go up to my demo and, well, fire up a new order instance to have 4 instances, or instances for all of them. This doesn't matter, because these consumer groups, this approach makes sure that everything happens, well, reliably, that everything will be consistent later on. And the Kafka cluster makes sure that all these are handled reliably and in order. That's important. And this is, well, how this works also when being able to distribute. And by doing so, well, I can distribute this approach then. And of course, again, I would use persistence in this case rather than that example to deal with this situation. So do you have any other questions for now the implementation? The question was whether it was possible to consume and produce binary data. Yes, it is. Right. In my example, yeah, not necessarily. I'm using string consumers, but I'm actually using JSON. So all my events will be produced via JSON, but that's just an approach. You can definitely do binary data. And, well, it depends how, you mean how big a single message could be? I would say, I'm actually not sure whether Kafka limits this, but I would say there is not really a limitation for that. So since, I mean, it's like an HTTP response, right? I don't know whether there are some, have to admit, I'm not sure whether there are some implications when you have megabytes of data or gigabytes per message. That's a totally different story, but normally I wouldn't say so, because that's a single message, right? There is not really a restriction. Now I would have a counter question, what kind of data are you sending? Because that should be an immutable event. If an event is, for example, image stored and you have a huge image, then it's, well, it's legged, fair enough to have a huge event. Then in your case I would see whether that approach, like for example with Kafka, supports it to have really huge messages. And I think it does. It only makes sense to split it up from a business perspective. If you say this is not really an atomic event because it consists of whatever, several things, then it's a different story. But if it's a single event that for some reason is huge, then it's fine, yeah. Yeah, thank you. Any other questions?
Hello.
Hi.
I'd like to know how you handle complexity of changing domain models. Let's suppose you have some complex microservices architecture.
Right.
And you have a lot of services that must be aware of events that happen somewhere.
Right.
And in that place, I mean the source of those events, they have, for example, change the model. So what do they have to do in order to keep the system consistent? Do they have to keep backward compatibility for the events they have published before, or some kind of, what else?
Yes, good question. So, first of all, it would make a lot of sense to be backwards compatible, yes, because then you can change a running system, basically, because you don't break things, right? So what happens? Several things here. You can basically change your domain objects, your domain entities, not the events, but your domain entities, if you, for example, reapply the logic. That means, in this case, what I'm doing here, I restarted everything and I recalculated everything. So for example, if in your calculation logic you want to change anything, you want to change how a coffee order looks like, so the things that are stored here, you can do so. Because you change it in your application, and then what you do, you restart and you rewind history, and then you recalculate how these things are calculated in this class here. And then, well, you have a new status, because you just throw away the current state and you recalculate everything based on your events in a different way. You recalculate in a different way, these events are still the same. That's, first of all, a huge benefit you can do with CQRS, because you can, well, rewind history and you recalculate it differently with a different domain model, domain entity model. If you want to change these events, yes, it would be advisable to do that in, well, backwards compatible way. If you cannot for some reason do that, like we had the other question before, then you basically have to throw away your golden source of truth and change the internal event store data and, well, restart it. But then you would not be able to do that in a zero downtime approach, because that really means you have to stop it and restart it from something different, because then it's not compatible anymore. And another important point for the microservice perspective you said, so in order to document it, in order to have an overview of what's in your system, well, it's important to document that properly. Because now what happens, if you want to model your burger order or your coffee order, you need to be sure that, well, you need to be aware of everything that happens basically in this whole use case. Because the whole use case, with all these three systems now model your business use case of ordering of coffee, right? You have to be aware of what all these three systems are doing in order to get the picture of your use case. Because if you look at an individual system, that's boring. You see, oh, accept order means validated, event, once this event comes in, I do this. Yeah, that's fine, but that doesn't tell you anything. You have to look at the overall picture to see, okay, that's actually the flow of information, and that's what happens. And that's very important that you document this properly, that you see the overall picture, and you need to be aware of all these systems involved. That's quite important. And yeah, again, what I mentioned before, for these reasons, for these overhead reasons, you only should do this if you really need to distribute, if you have to need to use this model. It's a very interesting model and interesting approach, how to deal with that situation, but you have to have the need for distribution, the need for microservices that are, well, communicated in a message-driven way. Because if you can avoid it, then please don't do it, avoid it. Because that's much easier. That's much easier to not use this approach. It only makes sense if you have the need for distribution, again. And then, do you have some more questions?
У нас, друзья, осталось время на один вопрос. Если у вас есть еще вопросы, Себастьян будет в дискуссионной зоне, можно будет обсудить это face-to-face. Вот. Последний вопрос из зала для трансляции, если есть, или уже в дискуссионной зоне. Видишь? Сейчас, секунду.
Okay, I want to ask, when we store all the events, we have overhead about amount of data we need to store. Could you say about your experience on real some application? Need we really big storage for that, or it's not so huge amount of data with ordinary CRUD application?
Very good question and very important thing. My experience is, don't worry. If a company says it does big data, no, it does not. Millions of events is not big data. So, no kidding, but normally from my experience it doesn't matter, because even in a big amount of data, for example, solutions like Kafka are able to handle them. That's my experience. Or even, not even Kafka, a relational database. No kidding, relational databases can handle much more events or entries than you can think of. Million is not a big number. Just one thought and, well, experience for myself, so what I've seen. And then to properly answer your question, it depends on the amount of data you have and on the data growth you have. So let's see, you have this and that amount of data, and your data grows from production data in such a big amount. And then you just have to look at the technical implementations that are out there, for example, Kafka, to see where it's able to cope with this data growth, and because then you can easily calculate how much data will we have in half a year, 1 year, 2 years, and so on and so forth. And then you will able to see, well, how much data we have then. Does this solution make sense? And well, you have to look in this specific messaging or storage solution you are using then, but from experience, it's usually not a problem in terms of data, amount of data. All right, then I can point you to, well, that project again, Scalable Coffee Shop, and also if this 60 minutes was not enough to fully get this quite new approach of CQRS, I also recorded a video course that's available for free under my blog in, well, several episodes, and you can watch them online on my blog for free. I can also mention my book again, Architecting Modern Java EE Applications, this one. And then, where are we? I want to say spasibo. Thank you very much for your attention.